Greetings, colleagues. Um, this virtual presentation was conducted by myself, Roy Clariana at Penn State University, and my colleagues, Tanya Engelman and Michael Kozlov, both from Germany. It involves the influence of graphical or textual lesson materials on team concept maps, and it also talks about a validation method that we use. Well, of course, concept maps are not a new idea. Here's an interview that was conducted in 2004 on NPR, and it was from an excerpt of a letter written by Jacques Reverat to Virginia Woolf in the north of Spain or the south of France, hard to say which, where he talked about concept maps, not as concept maps, but what a concept map is. Notice that he said writing he says that imagine this, in the middle of a large sheet of paper you could write a word and then radially around it write bits of information. And once you're done, you pretty much can see it all at once. So the idea of concept maps was in the jargon and in our conceptual basis all the way back to 1924. That's nearly 100 years ago. Alberto and Joseph in an article in 2012, they said concept maps consist of both content and structure. And so that's what we're measuring here is structure, a pretty straightforward way of measuring the quote, the structure that's in concept maps. And to, to show that this works, to help validate that it's an approach that makes sense, we took data from two existing studies that in one study, concept maps were used as the lesson materials, and in another study, text propositions that were exactly the same as the concept maps were used. And so in this way, we have two different kinds of lesson materials, and we will look at then the structure of the concept maps that are generated from these two different approaches and see if our measurement approach can measure it, and also what do concept what do team concept maps look like that are derived from other concept maps as opposed to derived from textual materials. Okay, here's two concept maps. On the left-hand side is the fully explicated experts map that contains all of the information. The right-hand side is the solution map. It's only the information needed to solve the particular problem that these students were asked to solve. As a general rule, what we found in this study, by the way, is that the groups that could not see others' maps, the COCA condition, tended to develop the fully explicated map like the one on the left. But when students were able to see others' uh, lesson information, then they tended to go straight to the solution map. Most important on this slide, I wanted to show the vector. Um, for instance, the expert on the left, if you find the term construction spruce in the center of the map, it's the most central concept, and you count the number of links that come in and go out, all of the links, you'll see that it's 9. So very simply, any node in a map can be converted into a value from however many there are down to 1, for instance. Or if there's a term that's not connected in the map, it's simply floating out in space, it could have a 0. It exists, but it could have a 0. And so what happens is that every map can have a node degree vector like this. Once you have node degree vectors, they can be correlated together, they can be averaged into group representations, they can be used in multidimensional scaling solutions, and all sorts of other solutions. So it's a very um, easy to understand and easy to accomplish way of turning a map into a mathematical representation that shows the most central nodes out to the least important nodes. The data is pretty clear. The groups that received maps as their lesson materials were much more their team collaborative team concept maps, their triad maps were more like the expert, that is the solid lines on this diagram, and also more like the solution relative to those triads that received lesson textual material. So there was a fundamental influence in the collaborative maps depending on whether they received a lesson text or a lesson map. All right, this data shows convergence. Convergence is quite an interesting metric in that it shows the relationship between a triad's map to another triad's map. So one concept map compared to another. On the diagonal of this chart, you see the relationship between a triad's map to other people who are in their condition, whereas off of the diagonal is the triad's map to those who are not in their condition and in their treatment condition. And what you'll see is the diagonal, the values are larger. There is, quote, convergence, that the treatment conditions led to maps that were more like those who had the same condition, experimental condition that individual was in. And so this is a very interesting metric that not the previous slide showed movement, psychological movement or mental map movement towards an expert. This map is showing mental map convergence of individual students, I'm sorry, with individual triad groups towards each other. Um, so both things are happening in this situation. This is the last slide. So the results align with what you probably would imagine is that teams that are given concept maps, they're the kinds of cognition that go on are more aligned with creating concept maps. We showed that this kind of vector data generated from a concept map, you can see how easy it is to collect, and we showed that this vector data then can be used for comparing to experts, to other benchmarks, and to other students, and to groups of students. So the these vector data are useful, and you can see from this data that they've shown that they work. And the last thing I think that's probably important, maybe most important, is it would be fairly easy to automate this within CMap tools, that vectors can be compared within CMap tools, or they can be outputted as vectors so that researchers could then put it into SPSS or some other statistical tool and analyze them using correlation or multidimensional scaling, and it would open up another whole line of research in terms of thinking about concept maps in terms of a very objective form of concept map.